do have a quick example.
So, number 42. If it gives me the vertices, I can find the lines.
Exactly.
And then I can find, should I find the area of that?
So you would do the points along each line segment, right?
Yeah.
When you do the analysis of your boundaries, you want to do one line segment for one side, another line segment for another side. So when you do your, when you get the equation of the line for each side, and you do your derivative and you find your locations where it's equal to 0, from your function, right? Once you plug it into your function, are you kind of with me? So let's see.
So here it's, so if I find a line that's 2 minus 0, so minus 0, so
Yeah, I always.
Yeah, 0, 0 to 2, 0. So you got 0, 0, 2, 0. And what was the other one?
That's better for the
0, 2. Okay. Well, it's even better than I was thinking. Cool. I like that. So this line segment is just x equals 0. This is y equals 0. So for each of those lines, you just plug that into the function. And the function they give you. Yeah. X squared plus y squared. Yeah. X squared plus y squared.
I always make my coffee super extra strong. Like I put more coffee in, and then
Okay. That's your F. So then you would say, okay, so if you're checking along this line segment here, you would set y equal to 0. So you get f of x equals x squared minus 2x. F prime, 2x minus 2. You get x equals 1.
it makes me stay really strong.
So it's 1, 0.
So that'd be 1, 0 because y equals 0.
Stronger. So I'm getting heavy and strong.
Then you do x equals 0 and do the whole thing again.
So I'll get 3 boundaries.
Then you do, and each one of them is going to be one you just throw to the function at the end to see which one makes it biggest. Right? You would,
and plus the critical points too, right? That's how I find out.
plus the critical points, yeah.
That makes sense.
Cool. Yeah, and then this guy you have to find the line equation, right? That's not too bad. Slope is 1, y intercept 2. Well, negative 1, right? So now I just plug a negative x plus 2 in here for y. But then, like I was saying, you have to actually also do x equal y, 2 minus y, and investigate that side too. The book might have made it so that they have problems where you don't have to do that. But I'm about to do one that shows you if you do it only one way, you only get one set of answers. This is a whole other set of answers.
Horrible, because then I would never be able to drink coffee again. Because I would be so much sugar. Don't drink it. It's gonna resolve
the 14th at 2:30.
Yeah. It's on the 15th? My son does.
You get it just
But his brother.
No, I checked it.
I don't know. So that's the right my family.
So guys, real quick, I'm going to do an example. Guys, and girls. I capture everyone. I'm going to do one example like what we just did. It's going to be relatively quick, hopefully. And then I'm going to talk a little bit about what the new method is. And if any of you have further physics to go into, this will become your best friend if you have to do any theoretical mechanics, possibly in your future. This method we're talking about in this section will become like your best friend. I can't say that enough. So we have this situation where I want to find the absolute max and min of this function, but the inputs I can use have to lie on this curve. Okay? So the way this is a little different than the one we did over there was I was allowed to use a lot more points over there, wasn't I? It wasn't just the ones that were on that circle, it was all the ones that were inside the circle too. So in one sense, this is actually a little bit easier. I only have to worry about the ones that actually lie on that curve, right? So who can kind of help me get started here? What could I possibly do?
So we just rewrite the logic and present and let's not.
Say again?
Can we rewrite that as like x squared over 4 plus y squared is equal to
We could.
1, and then do the fx of y equals 0 and start with
Now be careful. If I do fxfy equals 0, that'll show me the local maxes and mins, which might be extra work. All I care about are the absolute maxes and mins for points that must lie on this line.
and just find those points I plug in there and see which one.
Okay, good.
So
Right.
take the partial x and partial y first.
No, you
Not
don't
really.
have to go that far.
So if the points have to lie on this line, now just go with me. Let's do the easy way first. What's x squared have to be then?
4 minus 4y squared.
Right, cool. So then, let's do the x way first. So I know that x squared must be 4 minus 4y squared for any points I'm allowed to use. And I try to use the language that you know exactly what I'm doing here. This function I can plug whatever I want to in, but I'm constraining it. I'm saying I'm only allowed now to use points that actually lie on this ellipse. So I go ahead and use that in there. Right? Any points I pick, that must be true for. So how can I rewrite this then?
2 times 4 minus 4 is y squared plus y squared.
So now it's f of y. So then I can attack it directly with the derivative with respect to y.
What's the one with x?
Oh, that's the first way doing it with x's.
Okay.
Because the second way is going to be doing it with y.
Okay.
And this is really just to show you, you don't capture all your possible answers if you only do it one way. So here I get, what is it, 10 minus 7y squared? So now how do I find the possible locations of maxes and mins?
Take the derivative and say
I like it. So f prime, negative 14y, so what do I get?
y is 0.
Yeah, y is 0. So what's x got to be? Careful.
2.
Now let me ask you this. What must be true about my points? They have to be on what? Here. So if y is 0, x is plus or minus 2. I like it. So there's 2 critical points right there. Now, in one sense, it should kind of trouble you that I ended up with a derivative that only had y in it. So when I set it equal to 0, it's only going to be y equals 0. If I do this the other way, I'm probably going to have something that has only x in it. This might not be the whole picture. So do it again with y's now. Solve this for y and try to do it again for y squared. Don't go to y. You just need y squared, right? Solve it for y squared and try to do what we just did. So then you get f of x equals 2x squared plus this whole thing plus 2. And simplifying this a little bit, you get, what was it, 2x squared minus 1/4 x squared. Okay? 7/4 x squared plus 3, because the 4/4 is 1. You guys cool with me? And then do the same thing again. F prime is 7/2 x equals 0, which gives you x is 0, right? Which this dude didn't say shit about. Stupid little dude. Yeah, so if x is 0, then I get y is plus or minus 1.
Is that a 7/2?
Yes.
Oh, okay.
Because the 2 came down and killed part of the 4. Yeah.
Is the 4 minus 4y squared and f of y supposed to be squared?
Say again, sorry?
The 4 minus 4y squared, isn't it supposed to be squared?
Why?
Isn't it 2x
No, because
squared?
we were solving for x squared instead of just
Oh,
x.
okay.
You good? I'm not sure what you're talking
She was wondering why you plugged in 4 minus 4y squared.
about. Here?
Yeah. 'cause
Okay, cool. Just solving for x squared. Yeah, you don't have to go any further than that because that's what I have in there. Cool. And then what would I do with these? I mean, now it's the easy step. Plug them in, right? So f of 2, 0 would be, looks like 10, I think, right? F of negative 2, 0 is also 10. F of 0, 1, 0 plus or minus, because again, y is being squared. Looks to be 3, yeah. So your absolute max occurs in 2 places, which is fine, right? You can have a tie for absolute max. And an absolute min occurs in 2 places. Okay. How we doing?
Is that it?
Okay, cool.
So this only works if we have something that's not a circle, doesn't include everything, correct? It's only if everything's
Well,
on it.
this works, period, because this is the same thing we did over there. It's just that this was equal to, not less than equal to. It didn't say use all the points inside, too. If it said this, the change I would have made is I would have done fx and fy, because my first step would be, are there any critical points inside of there that I have to check out also? Now there is no inside of
So
it.
you only have
It's just on that boundary, right? And that's the whole point of this next section, actually, is as I walk, I'm thinking about Pulp Fiction all the time. As I walk in the valley, no, as I walk along my XY plane and I'm looking up, if I have to walk on a certain path, is there anywhere where the surface is the highest away from me or lowest as I walk along that path? Right? So we're slowly working our way along towards, well, that's going to come much later. So here's the new way to do this. And this is, like I said, this has applications in physics, most notably for me, because that's where I used it before. But I'm sure whatever subjects use physics also do this. And that would be these Lagrange multipliers. Lagrange, if you want to be all fancy about it.
Is that a song by ZZ Top?
Alright, so here's the idea. Let me draw that. Here's, let's say that this is some representation of level curves of a function. And let's say that, just for argument's sake, that these are increasing as they go out. Is that cool? So you guys can see what this would be shaped like, maybe a paraboloid or some kind of base flow like this, right? How we doing so far? So that's been smushed into the XY plane. So here I am walking along, roaming the Earth on the XY plane, and I can only move in this, what's supposed to be a circle. And you can see, now tell me, just looking at the picture, where is the maximum on that circle that I'm walking? Yeah, it's going to be right here. Right somewhere in there. I kind of made it flat on that side, but give me a little board license up here. Yeah. Okay. Do you guys kind of see what I'm saying? So if you were to, it would sort of be like this if I kind of pulled this back out, unsmushed it. It would be here I am walking in my circle, and somewhere there's going to be a maximum output, right? In fact, on this picture is actually behind it, which I can't make it turn around for you with 2 minutes. Now here's the thing. Somebody remind me the gradient. See, now I've got to bring it back in. The gradient, how does it relate to these level curves? Who remembers the basic relationship? Orthogonal, right? So the gradient at this point, it would be orthogonal to, orthogonal to the level curve. How do you think it's going to also be to the path that I'm taking? It's going to have to also be orthogonal there. And they go through this huge discussion about this idea in the book. They make it sound really horribly, terribly, like, wow. But if this, if that is the location of an absolute max, and I'm on this circle, if the gradient wasn't orthogonal, that means that I'm actually, let me see if I can get this all out. The gradient points you in the direction of steepest increase, right? Therefore, it kind of makes sense that it's got to be pointing out like that. If I've reached my absolute max, and I take any step, either back or forward on that path, where am I going to have to go on my level curves? I'm going to have to go like away from that, am I not? Right? If the gradient wasn't orthogonal at that point also, then that means that I should be able to somehow go higher somehow than I should be able to. It's got to be orthogonal to that point also. I mean, the picture kind of makes it look that way, but I want you to know I'm not just making it look like the way. It's actually got to be true. So these are the level curves of my function. And let me use the same notation they use here. Cool. Here's my so my function is g, and then my path that I'm walking. Oh shoot! I would do it backwards with that. My function is f. Make sure I do it the same way the book does. Then level curves of f. Now the path that I'm walking it on the xy plane. I can certainly look at it as if it's one level curve of a bigger thing, right? If I really wanted to. You guys with me on that? Sort of? So this is, I could look at it as one level curve of whatever this function is. And it specifically would have z equal to 0, because it's in the xy plane. You kind of stop right there, see if you guys understand. There's two things going on here. There's the actual function, that's f. And then there's the path that I'm taking. They got to give me another equation that tells me what path I'm walking, right? And that, in this case, would be g. So what's got to be true here is, like we just said, the gradient has got to be orthogonal at this point. So what must be true? If I have one gradient is pointing this way and the other gradient is also pointing this way, so this gradient is pointing this way, this gradient is also pointing that way. Which, how can you write that carefully? Would I just say this? Is that correct?
Equals the negative?
No, they're not pointing in opposite directions.
Can you say cross-coordinates?
Don't overthink it now. How do you know that two vectors are parallel? If one is 1, 2, give me one that's parallel to it.
They're multiples.
Ah, they're multiples of each other. So what in delta f have to be a multiple?
So A?
M or A you would think, but let's use the actual one that we use for Lagrange multipliers. Lambda.
Are you kidding me?
No. I did not just choose that myself. This is what has been chosen for us.
I like a weird vector.
You guys, where are my physics people? If you're going to claim you haven't seen that, I'm worried about who your teacher was or if you were awake. Because who remembers what lambda is used for in physics? Wavelength. Is the wavelength of light or whatever? For the rest of you guys, if you've never seen lambda before,
I have not.
there it is.
I've retaken
I've seen the
it.
movie before.
Really? Yeah.
Yeah, lambda, lambda, lambda.
I failed.
Okay, where's that?
I just stopped doing it at one point.
Not for that.
And I was
All right, guys. This G function right here, it's more than just my path. This G function is kind of like what this is a level curve of. Okay? Now, is there really a function G that this is a level curve of? No. But I need to establish this so I can take its gradient. Right? I need to pretend like it is something more than what it is so I can take its gradient. We've done stuff like this before. Didn't we have an equation like 0 equals x squared plus y squared minus z squared? We said this is one level curve of a level surface of a 4-dimensional thing so that we can do gradients to it. Same thing we've done before. Now, let's actually try a problem out because it sounds like I haven't actually given you enough to do a problem yet. Well, let's see what we can do. And in fact, we're going to do that last problem we just did. Okay. Let me leave this here. You guys all cool with this? You got that? You got that?
Yeah.
Yes.
I still don't get where the gradient G comes in. I know where the gradient F, that's the one, the purple one is looking at, right?
And the gradient G, if you want its own colors, is here also. I just don't know how long it
It's the
is.
same.
Yes.
It's at the max. It's the gradient at the max.
They must be the same. So the gradient of F and the gradient of G at that point must be the same.
I thought they had to be multiples of each other.
Well, it must be multiple. They must point in the same direction. What I'm saying in my head is yeah. They must point in the same direction. So they must be multiples of each other. They must be parallel to each other. I think I saw a better picture. Let's see, where is it? Yeah, okay. Let me ask you this, Katya. This here is a level curve of this function G, right? And its gradient must be orthogonal to the curve at that point. True? And the gradient of this function must be orthogonal to the curve at that point. And that's the point where they both kind of meet on that surface, right? On that line, they both meet there, so that those two gradients must be parallel to each other.
If that's a level curve, why can't I put the gradient somewhere else on that purple curve? I don't understand. It has to be in that spot.
So if I have, let's see if I can draw a better picture. If the gradient,
What do you think that'd be easier?
so if I really zoom in on this point, maybe this will help out. If I really zoom in on this point, I've got something like this really, right? So where would the tangent line be to this at that point? Wouldn't it match up with the tangent line of this at that point? So those two tangent lines match up, right? Is that better? Those two tangent lines match up. How does the gradient relate to the tangent line? Which is really why the gradient does what it's orthogonal. So that's why the black dude for F and the purple dude for G here, they have to be pointing in the same direction. They don't have to be the same magnitude, right? But they have to be the same direction. And this is really what that says. They have to point in the same direction, but one could be longer than the other one, or shorter, or whatever. Cool. Okay, sort of.
Yeah. I still don't understand why we're doing it at that exact point.
Oh, because this is sort of like when we started the last section, we talked about if I am at an absolute max, or if I am at a max, then this is true.
So we're looking at the max.
Yes, we're saying this is the max.
Right.
At the max, that must be true.
That's what I wanted to know. If we're just doing it at the max, or if we're doing it in each point.
So let me see. I want to leave this up here. I want to take this away. There we go. Cool. And doing it with this here. It's the same one we just did a second ago. Was it minus or plus 2? Right? And now, g of x, y is going to be my constraint, right? So f is the function I'm trying to maximize or minimize. G is going to be my constraint function. Yeah, so it's going to be x squared plus 4y squared minus 4. Now, look back at that example. What is x squared plus 4y squared minus 4 equal to in our example from before? It's equal to 0. So this thing is going to be part of what my constraint is. Can g of xy be anything it wants to be? It has to equal 0, doesn't it? So what I'm going to get here is, what is the gradient of f in general? I like it. Fx? Fy. What's the gradient of g? Gx, gy. Love it. Right? So how can you rewrite delta f equals lambda delta g a little bit more directly? I can write it as two separate equations, can't I? Fx must equal lambda gx. You guys see that? I'm just equating parts of the vectors. Fy must equal lambda gy. And then the last thing that I need, the last constraint that I need, is that g of xy can't be anything. It must be 0. I want that it truly to sit in the xy plane. Because that's me walking. I can't suddenly walk in the air. So I got to stay on that xy plane on the ground. So g of xy must equal 0. This is now a system of equations that I can solve. So let's see what happens. Let's see how this works. Right? This is kind of a freaky little bit of an idea here, but once you see how it works, it's freaking awesome. So what is gradient of f?
4x.
Okay, 4x.
And then 2y.
2y. And what's the gradient of g?
2x and 8y.
I love it. So then what are my three equations that I want to solve?
So 4x equals lambda.
Yeah, 4x equals 2 lambda x. Are you guys seeing where this is coming from? Because now delta f must equal lambda delta g. Because they have to point in the same direction. They have to be somehow parallel. So 4x equals 2 lambda x. 2y equals 8 lambda y. And finally, the third one is that you set g of xy equal to 0. It's got to equal 0. So then x squared plus 4y squared minus 4 equals 0. And why do I need three equations?
Because there is a free variable.
Because there's three freaking variables, right? There's x, there's y, and there's new dude, lambda. So on one level you might say, well, this doesn't look as easier. You just brought a new freaking variable in. Thanks, Jeff. But that's a hell of a lot easier to do here. That's a lot quicker. I don't have to worry about doing it two different freaking ways. All this shit is kind of built in. So solving number one, what do you get? If he's trying to solve for, actually solve for lambda, yeah.
Lambda equals 2.
And be careful, don't solve, I gotta be careful how to say
Don't
this.
use x as like a.
Try to factor this guy out. So if I divide by 2 and subtract this, let's subtract this over this way. I want to get lambda x minus x, minus 2x equals 0. You guys with me?
Wait, what?
Divide by 2.
Okay.
Subtract this over here.
Okay.
So good there.
Okay, and
Take an x out.
x.
What are your answers to that? There's two variables there. X equals 0. Lambda equals 2. Cool. Now look at number 2. What does he say? So if I do the same thing, I'll get, subtract that over, divide by 2, I'll get y times 4 lambda minus 1, right? Good, so y is 0, or lambda equals 1/4. So now, the third equation doesn't have a lambda in it, which is nice. You can just plug the x in there, see what y is, plug the y in there, see what x is. You can plug into here the other lambda, you can plug in here the other lambda. So now you just got to play around with all the possible ways you can plug stuff in. You're always going to have one equation with no lambda in it. That's kind of nice, right? What's got to be true is they all have to be true simultaneously, though. So if I take x equals 0 and plug it in here, let's just get the easy stuff out of the way first. If I plug x equals 0 and plug it in here, what do I get? 4y squared minus 4 equals 0. So y equals plus or minus 1. And if you plug in y equals 0, yeah, you get, what was it trying to be again? 4? Yeah. X equals plus or minus 2 when you plug in y equals 0. So just keep track of those. What are we doing so far? Okay. Now between the first two. Take this away. Cool. If lambda equals 2, looking at the second guy, what's that mean about y? So lambda equals 2 for the first guy. Plug it in the second guy. And there's really nothing else than y equals 0 you can get from this, right? So these two will only give you y equals 0. So I just want to put this up here because in general you do have to kind of check this out. And the first one, the same thing's going to happen. The only thing you can really get from that is 0 for x. 4x equals 1/2 x. X is 0. So then what are my answers then? Did the lambdas actually end up giving me anything new? No. That's okay. What are my answers then?
Are you looking for points?
Yes, cool.
So
0, 1, 0,
0 plus or minus 1, right? And plus or minus 2, 0, right? Which if you look back to the earlier one, isn't that what we got?
Yeah.
This problem when we did this earlier?
Yes.
0 plus or minus 1, plus or minus 2, 0. Cool. Right? What's that?
So how is this easier?
Trust.
Just so much work.
Is that a 4x equals
That was
1/2?
supposed to be the easy.
Now, that over there, did I actually have to do that?
No.
And this problem, no, because I could see that the only possible answers I'm going to get from those are 0.
But is that 4x equals 1/4 or 1/2?
Lambda.
1/2. Once you plug a lambda in of 1/4, you get 1/2.
Okay, 1/2.
When you have like 10 critical points coming from a problem, it's sort of like when you first teach students matrices, and you have to do a 2x2 matrix. And I don't know if you guys remember doing this at all. When you try to solve a system of equations using a 2x2 matrix, it actually is more work. When you do a 3x3 matrix, it's about the same amount of work. Any larger system of equations after that, the matrix kicks by hand's ass, right? So here, this is a relatively small problem. I really only got 4 critical points, which in the scheme of things is a small number of critical points. So if I do it the other way, there actually was less work over there. It just took me a little while to explain it. There was really less work to do over there. If you get any more critical points that would have come out of this, that one definitely beats this guy's ass. Right? So if I made a more complicated problem, that way would be a lot critical. And there are problems that you can't do this way that you can do this way. That's another good reason to know how to do this. Let me see that. Let's try it. Let me see that. One more here. Oh, cool. Perfect. Let's do one in 3 variables, and then I think we'll call it a day. Example 3 in the book. Maybe not. Example 2. Now, one key thing about this problem, remember the f function is the function I'm actually trying to maximize or minimize. The g function is my constraint. So, this point is set. What other points can I compare that point to? Where must they be? They must be they must work in that equation. They must sit on that, what turns out to be, like if you look on page 868, it's that cone that goes in both directions, right? So this is going to be related to somehow my f function, and this is going to be my constraint function. That's my g. What's the actual f function itself? And it pretty much gives it away. What am I trying to make small or make big? The distance, right? So what is the distance formula? And don't worry about this. Don't make this harder than it is. It's just funny. I was waiting for somebody to giggle about that. I don't know how you do that, but you don't have to pull into your function anything about your constraint function. Those are just the points you're allowed to use. So really, I want to know the distance between this and some point where that point happens to be sitting on this image, right? Sitting on this cone going in both directions. So what is the distance between x, y, z and 3, 4, 0?
X minus 3 squared plus y minus 4 squared plus z squared.
X minus 3 squared plus y minus 4 squared plus z squared, right? And the nice thing is, can we all agree, I think maybe you've seen this before, in general you just don't do the square root, because if you maximize or minimize those, you obviously maximize or minimize the square root, right? How are we doing there? Thank God I don't need a square root in there when I got to do all these derivatives. So that actually, instead of d, let me just say that's my f function. Cool? So how can I write my constraint function a little bit better? What's g of x, y, z? I like it. X squared plus y squared minus z squared. Right? Okay. Yes?
What's gonna be the difference if we say z squared minus x squared minus y squared?
Not a single difference at all.
Not different?
No difference. No difference. Because it's just coming at it one way or the other way. And really, in the end, you're going to constrain it to equal 0. So either way you look at it, it's going to have to come out to be the same thing. So you could have pulled everything out the other way. I don't care. So one constraint is going to be the one that you can always have. It's going to have to be g equals 0. So you're going to have x squared plus y squared minus z squared equals 0. That's one constraint I always have. I don't really have some general g function. It only exists on the xy plane. I've got to equal it to 0. Well, in this case, it's surface because I'm in more dimensions. But what do I need to get then to finish this out? The gradient, right? I know that the gradient of f has to equal lambda gradient of g. So one thing I can write is fx must be lambda gx. Fy must be lambda gy. And now I've got another variable, so now fz must equal lambda gz. Or just enough of that to know that I ain't good.
Instead of easy, it's cheesy.
So what's fx?
It's 2x minus 6.
I love it. See, the 2 just comes down, so you get 2x minus 6 must equal lambda times gx, 2x. How are we doing? I mean, that's why this method is so much easier. Because the ones we did the other way, this constraint was actually relatively easy to work with. They didn't have to be. They could sit on square roots, and they could sit on natural logs of crap. Right? That would be really difficult to figure out how to make those things go together really easily. Much better just go ahead and do some straight up derivatives. I mean, I can always do a derivative. I don't care what the function is. Fy, same way, right? 2y minus 8 was lambda gy 2y. Fz, so z must be lambda